Okay, so the first speaker this morning is Tom Sanders, and he's going to talk about Roth's theorem on arithmetic progressions.
Thank you very much. So just a couple of elements of housekeeping to start with. I'm afraid I'm using my phone as a timer, I'm not expecting a call if I'm looking down at it, okay? It seems also maybe I should have given a slide talk here. I'm going to give a Blackboard talk. So if my writing starts to get very small and you can't see it on there or there, just give me a shout. I will try and write as large as possible. So the talk, I guess, will be about 55 minutes, and I want to focus quite a bit on motivation for the problem. So as was said, I'm going to talk about Roth's theorem on arithmetic progressions. So a starting point for a conversation about this could be the result of Green and Tao from about a decade ago on arithmetic progressions in primes. So I guess this is well known, but let me start by stating this. So they showed that the primes contain arbitrarily long arithmetic progressions. Okay? But actually, the case of length 3 arithmetic progressions, as I guess most of you know, was proved a long time before that by van der Corput. Showed the above for length. Okay? Maybe 70 years or so before that. But I guess it wasn't a completely satisfactory resolution from a certain perspective, because certainly in this talk and to my mind in many situations, the purpose of a proof or an argument or a result is somehow to explain the why and not simply the that. I'm not sure it's necessarily particularly exciting that the primes contain arithmetic progressions or don't, but somehow what we're interested in is why. And I think certainly around the time of van der Corput and a little bit later, this was a question of interest to people then. And indeed, they formulated a sort of question which is somehow saying, well, maybe the primes contain these arithmetic progressions just because there are lots of primes. And so lots, in this sense, means somehow some sort of large proportion of the numbers 1 up to n are prime, so that'll give you a sense of what I mean when I'm using the word large. So that was maybe I'll move over. So that was the question, was do the primes contain 3 APs simply because there are many of them. And then in the 50s, Roth approached this question by proving the following result, and I'll explain exactly how it relates. He said that, so suppose that A is a subset of 1 up to n, containing no 3 APs, then A has size little o of n. So the density of A, say alpha, is little o of 1. So I mean here little o as big N tends to infinity. Okay? And so the point is, if this little o tended to 0 fast enough, then this would capture the primes. So if he'd shown, for example, that mod A is little o of n over log n, then we know, say, since Chebyshev, that there are at least n over 100 log n primes in 1 up to n, and you would have this fact for free just because there are many primes. Okay, so in some sense, it would turn out that the property of having 3 APs, so 3-term arithmetic progressions, would have very little to do with the primes. Okay? So Roth, in actual fact, showed n over log n. And then there are various improvements. So Heath Brown and Semerady independently showed that there was a power of log that's omega is just supposed to be some constant, so say 1 over 20 or something like that. So it's not a horrific constant, but it's and then Bourgain showed an explicit constant, basically, of a half minus little o of 1. And I will talk a little bit about what I will talk a little bit about that later. Now we know sort of the most we could know without answering the original question. It's a little bit disappointing in that way. So we know that under this hypothesis, so A is a subset of 1 up to n, containing no 3 APs, then A has size, well, n over log n up to some power of log. So, as I say, what you want is sort of, you want any power here better than 1. Okay, so this is the most you can say without answering this question. Okay? I should perhaps clarify here. I say no 3 APs, I'm talking about non-trivial ones. I don't count 1, 1, 1 or something like that as a 3-term progression. Okay? And so then I should mention somehow that maybe I can pop in here. Erdős and Turan essentially conjectured yes is the answer to this question. So the way that they happen to express their conjecture isn't exactly in this density language. What they say is, suppose you have a set of integers such that the sum of the reciprocals of those integers tends to infinity, then that sequence contains infinitely many 3-term arithmetic progressions. It turns out for this sort of problem, once you have kind of a sensible argument for finding 1, you have a sensible argument for finding many, basically by averaging. And I guess, I don't know exactly, well, I should say a number of things. So first of all, this is not universally accepted as the name for this conjecture. There's a big discussion page on Wikipedia if you want to find out people's thoughts on that. But it is sort of, in practice, people will know what you mean. And I guess also they chose to state it as this sum of reciprocals things because I'm told that one of Erdős's favorite results, or favorite facts he discovered when he was prodigiously young, I imagine, was that the sum of the reciprocals of the primes is infinite, or diverges. So I think that's what they had in mind somehow. They had in mind this question up here. Okay. So, let me talk then for a little bit. So that's a little bit of motivation. We've got this question, and somehow we want to know what the real answer behind it is. I want to talk a little bit now sort of about lower bounds, how good we could expect this thing to be. And then a little bit more about generalizing in general, generalizing this problem further, and then a little bit about actual approaches. Okay, so that's a rough plan for what I want to talk about from here. So, lower bounds. Okay. And so this is really a well-known construction of Berend. And it gives some kind of argument from a different direction as to why this problem should be maybe not completely trivial. Okay, so Berend showed that there is a subset of 1 up to n with no 3 APs, and such that it's very large. Okay, has density basically e to the root log n. So, and this constant is actually known. Okay, this will. I'll mention that later, actually. Okay, so it's a kind of funny shaped bound, and you see also, right, somehow it's very far from the best upper bounds we have are very far from this lower bound, right? They're basically out by an exponential. Which, given the range of possibilities in this problem, is basically out by as much as it could be. I do kind of want to mention, although, I mean, so this is stuff from, I think, about 46. I do just want to mention the idea here, because the idea is quite easy to understand and quite geometric in actual fact. So, to be completely clear, right, we're now moving completely away from the primes. Okay, so the primes A would not give an example of this, because we know by van der Kolk that they do have many 3-term arithmetic progressions. But so this will be a completely different shaped thing. And the idea from this is that if you take a convex body, strictly convex body, and you take 2 points on it, then if they're in arithmetic progression, say, thinking in arithmetic progressions in R to the D, well, if you like, any third point that makes up an arithmetic progression can't actually be in that set. So just suppose strictly convex body, for example, a circle. So, well, either the point, the third point in the arithmetic progression is there, or it's there, or there, right? Is that right? Yeah, so it's either that, or that, or that. And in any case, the third point is not in the circle. Okay? And all I'm using there is the fact that it's strictly convex in some way, right? So, if I were in R to the D, and I wanted to construct a set in R to the D, that's one way I might do it. I might take the surface of a convex body. Okay? And that's basically exactly what Berend does. He says, well, okay, I need a discrete number of points, so I'll just approximate R to the D by a lattice, a very fine lattice, ZD, and I'll take a d-dimensional sphere, And really I'll take a little shell here, so this is in r to the d, and I just take some sort of delta width shell, and I intersect that with some lattice in z to the d, and this sphere lives inside the d-dimensional cube, and I can project the points in the d-dimensional cube into 1 up to n just by imagining that they're written in some base, some large base, let's say m. Okay? And if you do that in a sensible way, I'm not going to do the details, but I want to give you somehow the idea. If you do that in a sensible way, you get some large set in 1 up to n, which still preserves the property of not having arithmetic progressions. Okay? And if you optimize the constants, some people, I'm about the level of laziness where it's going to be a big O here, and some people can make that big O into an actual number, and you can go on from there. I should say the bound has basically been static since Berend, although there's some slight improvements due to Elkin, which were the proof was re-expressed and improved by Green and Wolf. I mention this example because if you feel like zoning out later on, you can sort of try and improve it. It's one of those things where it's a sort of problem that you immediately think, so I should try other convex bodies somehow, not the sphere. I guess like every PhD student who studied this question has gone through that process. I certainly did. And they're not any better, but it somehow feels like they will be. It's a sort of nice and nasty problem at the same time. It sucks you in very easily. Okay. Now that construction, and particularly the fact that it's the sort of best thing we know, in a certain sense suggests that this problem really has very little to do with the primes. Or you might, maybe not suggest is a strong word, but you might feel that it lends some weight to the idea that it might not be completely related to the primes. And in some sense that's true. So it may well be that just sort of large subsets of Z have this property of having 3-term arithmetic progressions. But it may be that you don't even need the group structure of Z. In actual fact, this may really have very little to do with the integers at all. So there's another result I want to mention called the triangle removal lemma. Now, this is a result in combinatorics. That I want to state, and then I'll sketch to you roughly how it can be used to imply Roth's theorem. And you'll see that it's a way of somehow completely removing the group structure from what's going on. And yet this example still applies. So this says, suppose G is a graph. So just remember I know I'm not talking to a combinatoric, so it's just a bunch of points and lines between them, right? But not necessarily in the plane. Containing, let's say, a graph on a vertex set of size n, containing at most delta n cubed triangles, then we can delete epsilon n squared edges from G such that all triangles are removed. Okay, so let me just let me explain that, because I know this is, there's some details here. So the vertex set's just a number of x's in your graph, just a number of points in your graph, right? And a triangle in a graph is just, if I've got 3 points and I've got all the edges between them, right? It's what you think it is. That is a triangle. Okay? So if I've got n vertices, I can have at most n cubed triangles, right? I mean, maybe not even quite that many because of symmetry, but let's say it's roughly n cubed. So this hypothesis is saying somehow I have not very many, I have a small number of triangles. Okay, so think of delta as being something tending to 0 slowly with n. Okay, so maybe delta is 1 over a billion or 1 over a squillion. Okay, so I've got very few triangles. Then, I should have. Of course, the point is, epsilon tends to naught as delta tends to naught. Now, then I can delete. So how many edges have I got in total in my graph? Well, at most kind of n squared, right? I can at most pair up any two things. So this is saying I can delete some small proportion of the edges such that the resulting graph has no triangles in it. Okay? So you might imagine a situation where I had loads of vertices, a sort of tripartite situation. Okay? And I connect everything here, everything here, everything here, and then I have lots of triangles, okay? But if I only connect a few things, let's say like a couple of things here, or 3 things here, then I don't have many triangles, and indeed, by removing those edges, that's a small number of edges, I end up with a graph that has no triangles. Although the graph itself does have many edges still, right? Because it has all of these here. Okay? So this is a result due to Ruja and Semeridi. Okay? And the question somehow is how quickly can you force epsilon to tend to 0 with delta? So they show epsilon is something like 1 over log star delta inverse. So log star is the number of times you need to take the log of a number to get it below 2. Okay? It is a ludicrously slowly growing function. It's the opposite of the tower function. Right? It's a nonsense function. So this thing, this is feeble. I can't stress enough how bad this dependence is. Okay? There's that sort of analytic number theory joke, isn't there, about log goes to infinity but has never been observed to do so. Well, log goes to infinity so much faster than this guy. This guy's, slower than any iterated set of logs, right? I mean, really, I want to, very poor, okay? And that's more or less the best we know. Okay, so the dependency here is very, very weak. The point is the dependency there's no dependence on n. Okay, so how does this relate to Roth's theorem? Well, suppose I have a set of, maybe I'll go and rub out over there. Suppose I have a set of, a subset of 1 up to n that contains no non-trivial 3-term arithmetic progressions, where I remind you that trivial is just where the common difference is 0. Okay. So then, suppose I'm okay. Well, then I just let 1 up to, I guess in this case, I probably want 2n, be my vertex set. And basically I connect in G if x minus y is in A. Okay? That's not exactly what I do, but that's roughly the idea. Okay? You embed A as a Cayley graph. Okay? And then if you go through and examine what you have a situation where the fact that you have to be slightly careful about how you do it in actual fact, and you're better off making it tripartite. But if you do it in the right way, you will find that the fact that you have no 3APs that are non-trivial means that the only triangles that come up as being trivial triangles, and there are very few of them. Okay? And so then you find that you could delete some small proportion of edges, which corresponds to deleting some small proportion of A, if you do this carefully, such that you have no triangles. But if A contains even one element, then it will turn out you have a trivial 3-term progression, which will force you to have a triangle. So the process of deletion here must actually have removed every edge. Okay? And that means you can't have had many edges. I don't think I've given quite enough details there, but I don't want to drill down into that anymore. It's not a super complicated exercise, but maybe I'll leave it as that to find this equivalence. And so what you have then is a situation where, in fact, Roth's theorem follows from this. The best known construction we have from this is basically this Berend construction here. So it might be the case maybe you can get epsilon is e to the minus big O of log squared delta inverse root log to the 1/2, so something much better. Okay? And that would be quite nice, right? Because somehow you would have a situation where you would have discovered that these 3-term progressions, although you, I suppose, need a group structure to define them, you don't need very much. You only need some fragment of a group structure. To define a 3-term arithmetic progression, I don't actually need to be able to add as much as I like. I've only got to be able to add elements together about twice. Right? I need to be able to form x plus y, and I need to be able to form something like 2z. So you could think of some notion, for example, a local group, where I have some restricted amount of the time that I can add, would have enough sort of group structure to force a result of this type. Okay, so these guys are very they're very insensitive to there being a global group structure. Okay? Good. Okay, but let's return to the integers. And let's talk a little bit about now how you can think about this problem. So if this last bit of waffle about the triangle removal lemma is not worked out for you, you can come back online now, because we're not going to chat about that anymore. I just wanted to sort of emphasize somehow that, when you're thinking about these arguments, you may not want to use too many properties of the integers. Okay. So, a natural question, if you're trying to think about this, is when is it easy to show that A contains a 3AP? Okay? So you imagine a situation, you're coming to this problem, you've got some subset of 1 up to n, and it's dense, you've got 1% of 1 up to n, and your objective is to show that there is some non-trivial 3AP. Okay? And so you start, maybe you think, okay, I have no idea. You start to think, well, which sets can I easily show this for? Okay? And remember, we're looking at something that density is some sort of global property in this case, so we're probably not going to be very interested in just locally adding in a 3AP. So clearly, given any set, I can make it into a set with a 3AP by just bolting on 3 elements, right? Or in actual fact, almost certainly just bolting on 1. But that's not an interesting way of doing this, okay? So, well, let's suppose, so there's the example that we like to start with is the random case. So suppose we choose x in 1 up to n to be in A. With probability alpha. So alpha is somehow naturally the density of A. So we then, well, the expected size of A is just alpha n. We're choosing them independently. And now, if we write T of A for the number of three-term arithmetic progressions in A, well, then the expected value of T of A, well, there are basically 2 types of progression, right? There are these ones where there are 3 different elements, okay? Now, how many of those are there? There are basically, they're roughly n choose 2, but so let's say about, there's about n choose 2 of them. And the probability that any one of those survives is just alpha cubed. And then there's some annoying error term, right, which is just all the trivial ones. There are n of them, and the probability that each of them survives is alpha, because it's just one element. So let's forget about the trivial ones for the moment. The main point is you've got about n choose 2 3-term arithmetic progressions in 1 up to n. And the chance, if you're picking your elements independently at random with probability alpha, the chance that any one of those things survives is, well, it's just alpha times alpha times alpha. Okay? And so linearity of expectation then tells you this is the case. So let's write this as alpha cubed n squared over 2. Okay? So let's think about this. For A to have no, if A is quite dense, right, then A has clearly lots of non-trivial arithmetic progressions because there are at most mod A trivial arithmetic progressions. So provided that T of A is bigger than mod A, you expect A to have a non-trivial arithmetic progression. Okay? So that gives you some bound, right? If, and I'm not being careful here, but suppose now, typically, I mean, you've got some sort of concentration phenomenon, right? So typically I can pick this to be within, 100 times the variance of this quantity of the mean, and this in the same way, and that will happen with massive concentration. So let's just suppose I've picked them so that T of A is about this, and the size of A is about that. So that gives you this translates to this in this case. And that gives you some condition on the density, right? Okay. That's a very rough and ready calculation, and this is not a good way to do it. But the point is that this suggests that in the random case, unless the set is very sparse, you're likely to have these three-term progressions. And actually, just as a sort of point of interest, as you've probably appreciated from my earlier remarks about triangle removal, this Roth's theorem has somehow been approached from both the number theoretic side and from the combinatorial side. So the number theorist, obviously, with the primes, you've got some sort of idea about, well, there's some reasons that some of the aspects of this are going to be hard. You know that the bound can't, whatever bound you get in Roth's theorem can't trivially be that good because somehow van der Korput's theorem takes some level of effort to prove. And you assume that he didn't miss a trivial trick, which is sensible. And the combinatorialists, on the other hand, think, well, basically everything, or certain type of combinatorialist thinks basically everything in the world is random, so this is the worst case. So in fact, this should be they come at it expecting a polynomial bound, and somehow the bound is somewhere in the middle. So you have both camps sort of coming at it from a different angle. But this bit here converts into a proof. If you formalize somehow this notion of choosing at random. So you might reasonably say here, well, okay, fine, you pick a random set and has lots of three-term progressions, well, big whoop. A sphere doesn't look anything like picking a random set. So what? Well, you can formalize the notion of looking like random. Okay? So you can define a norm. And I'll tell you one candidate in a moment, such that if the indicator function of A minus, and I'll explain why I write it like this, right. So some norm that will measure, and what it's supposed to do here is it's supposed to measure the distance of the indicator function of A, from the indicator function of A, to what it would be if A behaved just like it were picked at random, okay? So just on a very rough level, I'm going to drill down into some more details in a moment, but at a very rough level, this is somehow measuring the distance of A from behaving from random in this norm, and that will turn out to imply that in this particular, with this particular quantity T of A here, T of A has close to the right number of three-term arithmetic progressions, with this error here that's dependent on epsilon, okay? So one way of defining this norm is just as the spectral radius of the convolution operator, which you can also define using the Fourier transform. Okay, so this is something that we're very familiar with in analytic number theory. So that's supposed to be the circle here. This is just the Fourier transform of f at theta, or the exponential sum, if you prefer. Okay, and as I said, so this is sort of this is the spectral radius of the operator G maps to F star G from And obviously, again, this is the sort of guy that's been studied from all sorts of different perspectives, right? I mean, this is studied, well, the group guys like this, and the combinatorics guys like this, and number theorists like this as well. Okay, and so it turns out a little calculation that we'll see in a moment if time will show you that that if this, in the sense of this norm, is small, then this happens. Now, there's a slight problem here that I'll mention later, which is that this is sort of not exactly the right thing to define for this problem, because what you would really like is 1 up to n to actually be a group, because the Fourier transform behaves better on an actual group, and really it behaves just approximately like a group in a way that will be quite informative later. Okay, so what this gives you is a way of saying that in some sense if A looks random, or if A is close in this norm, then your set A behaves like a random one, and we're done, okay, based on this calculation. So the alternative somehow is that this norm here is not small, okay? So that would tell you somehow that f here correlates with some linear factor, this exponential here. And then there are various approaches, okay? So Roth's original approach then said, well, in that case, you can find, so Roth showed that if this guy is large, so then there is an interval of length about root n such that A has bigger density on the interval. So let me again explain this. So this epsilon here really, well, how would you pick epsilon? You pick epsilon, right, so that it's, in this case, I suppose, about alpha cubed over 1 billion or something, right? So that this really is an error term. So epsilon really here does depend on alpha. And if you do it in the right way, in actual fact, you can make it an alpha squared using Parseval's theorem. And so if you think of this as depending on alpha in a sensible way, then somehow it's not a surprise that none of this, the root n and this guy, doesn't depend on epsilon. Okay, so you might be worried here, I've introduced an epsilon and then my conclusion doesn't seem to depend on epsilon. Really, my epsilon here is alpha squared or alpha cubed. Okay? So you have a situation where you've got a shorter interval, but your set has larger density. Okay? On that interval. So it's not got, I've not created points from nothing, but I've said locally, I've got better. Okay? So if I'm not uniformly distributed, if I don't look random, then there's some interval on which I'm doing better. So of course, you can just iterate this process now, right? And this is very common for this kind of problem. So I just keep going. Now I'm looking at this new. Of course, it's not an interval, it's an arithmetic progression. But it's arithmetic progression in not the sense of being a 3-term arithmetic progression. It's a very long arithmetic progression. Sorry. But morally, it's an interval. Okay? Because, now, and why can you do that? Well, being a 3-term arithmetic progression is affine invariant, right? It's dilation invariant and translation invariant. So I give you some other arithmetic progression on which I have higher density. If I find a 3AP there, then I also find a 3AP in my original problem. Okay? And that's a really important property. So for example, these sorts of arguments don't work if you want to, instead of solving the equation x plus y equals 2z, and that's basically what we're doing here, right? You find a 3AP in the set A is like solving this equation with x, y, and z in the set A. Okay? But if I remove the 2, well, I can't hope for these arguments to work. Why is that? Because, well, if I just take the odd integers, right? There's loads of odd integers. I mean, really loads, not primes loads, loads. Then odd plus odd is not odd. So something about this argument would have to fail, and in fact, it's this inductive step. So, and let's just, I told you Roth's original bound was about n over log log. So this sort of, you can't have density bigger than 1. So that means that this kind of iteration, it terminates in actual fact in about big O of 1 over the density steps. So about 1 over the density of steps, and game over. So that means you have to have square rooted about alpha inverse times. So that means somehow you need n to the 1 over, you need n to the 1 over 2 to the alpha inverse to, say, still be bigger than 3 or something. And that gives you your bound on alpha of the log-log form. Okay. So Roth appreciated somehow he had to produce a self-similar object, this sort of, that these arithmetic progressions are similar to the original interval. Okay? So a general mechanism for this is an induction. And a general mechanism for improving inductions, right, is if I can somehow enlarge the class over which I'm inducting. Okay? So that was, in some sense, Bourgain's observation. Or, well, it's more than an observation. But, what he said was, well, actually, you don't much care that this is an interval or even an arithmetic progression. There's some more general thing, in particular a Boar set. So let me be precise about that, actually. So a Boar set in 1 up to n is a set of the form. There's a subset of 1 up to n. Such that, now, so this here is these, I'm now using this as fractional part, those bars as fractional part, right? So it's just a set of x in 1 up to n, where x times some theta 1, which is in the circle, is within delta of 0, all the way up to x times theta d is close to 0. It's basically a d-dimensional cube, right, embedded in 1 up to n in a sensible way. Okay? And the one-dimensional case, if you just have little d as 1, that's basically a long arithmetic progression. Okay? That's not quite true, but it's basically that's the deal. Okay? That's how you want to think of it. And then these are, you want to think of it as higher dimensional arithmetic progressions. Now, what Bourgain noticed was that actually all of this sort of chuff here that I've meant, this, in particular this fact, this holds not just for intervals or groups, but it holds for these Boar sets or approximate groups. Okay? And I'll be a little bit more precise about that in a moment, the notion of approximate group there. And so he said, well, okay, in actual fact he noticed that this argument here tells you that if this is large, then you in fact have increased density on a Boar set, but that Boar set is much bigger than root n. So he showed, this is very sketchy here, by the way. I kind of want to give you more of a feeling than the details for this sort of stuff are an absolute nightmare. So, but I want to give you a sense of why. So then there exists a Boar set B. Let me put a D in there and I'll tell you what I mean by that later. Such that B is large, and get the same density increment, actually. Okay? So it's the same density increment, but on something that is much larger. Sorry, let's call this an I. Now, the I there is, if you've done this I times already, then you get an I there. So the first stage, this is just some constant. Okay, I get a Boar set. But then when I repeat all of this argument relative to my Boar set, then instead of one in there, I get a 2. And then I get a 3 and a 4. It's some extra cost, okay? But it will give you a bound of that form. But what you find is that these Boar sets are ultimately much bigger than these progressions, okay? And because you found this much larger object, you have a much more efficient induction. You get a much better bound, okay? So this is part of somehow another way of generalizing this problem, which we have actually captured already, but not in detail, which says that somehow what we use in this argument is Fourier analysis or exponential sums or whatever, and in some level, the Fourier transform exists for our purposes is just a way to diagonalize the regular representation. Okay. And you don't actually care that it diagonalizes, you care that it gives you some kind of singular value decomposition. Actually. It's something more. So diagonalization is sort of algebraically a little bit sensitive, right? This is very analytic, it's a very robust problem. So you clearly can't care about whether it's diagonalization or whether it's something that is slightly easier to perturb, and in fact it is slightly easier to perturb. But what it turns out, because we're doing this robust thing, is that it is enough to have an action or a way of convolving so I'll explain what I mean by this, is to have it's enough to have the following setup, okay? And this is what a notion of approximate group is. So the following setup is a pair, BB prime, and the picture you have in mind here is big ball, little ball. Okay? Now, this sort of behaves like an asymmetric. I want to think of these as behaving like an asymmetric group. So just think in R to the D, right? Big ball, little ball. So if I've got a big ball in R to the D, and I add something from a little ball, I basically always stay in the big ball, right? Because there's just, most of the time I'm, say, here, and I just move over a little bit, and I'm here. Well, I'm still happy, and I can, it's great most of the time. Unless I happen to be a pain in the neck, and I wander up to the boundary, I don't fail to have closure. Okay? So it's a sort of asymmetric way of adding. You can add one thing from a big ball to one thing from a little ball, and you basically stay in the big ball. Okay? And that turns out, so then you can use that to define some kind of way of convolving measures supported on the little ball with functions supported on the big ball. Okay? So this is not perfect, but if you restrict to B, this is some kind of approximate way of putting an action of this space on that space. And that's enough, sort of simultaneously diagonalizing all these actions, which is what the Fourier transform does, is enough, that's enough of the amount of the Fourier transform we need to do these kind of arguments. And that's why, so that's what Bourgain in some sense did here. He said these Boar sets, which are basically high-dimensional cubes projected into 1 up to n, well, of course, it's no big mystery, right, that a high-dimensional cube for this purposes behaves the same as a high-dimensional sphere or high-dimensional convex body. And that was enough, in some sense, to provide the strength of the Fourier transform to run this argument. Okay, so in the last few minutes then, where do you go from here? So if you work out these details here, this gives you this bound in Roth's theorem that says alpha is bigger than n over root log, roughly. Okay? Your problem every time can be summarized exactly by this picture here. Okay? Your problem is that if I give you a big ball, to do any work, you have to immediately form the small ball. Okay? So you have to, if you want to treat this like a group, once I've given you the big ball, you've got to dilate it, and that's the other that's the pair to produce your set B prime. And the problem is all these arguments, you sort of, if you like, the action what you input gets inputted on the big ball, and what you output gets outputted on the small ball. Okay? That's a very rough sense, but what it means is every time you run this argument, you have to somehow dilate your ball each time. Okay? And that is what gives you this factor here. Okay? The fact that this factor is increasing with time is a result of having to repeatedly dilate. So if you want to improve Bourgain's bound, what you actually have to do is find a way to run this argument, some version of this argument, far fewer times. Okay? So this runs too many times. Basically, it's too expensive because it runs too many times. So you have to form some way of running it fewer times. And that's not completely trivial because, and this will be the last thing I say, there's a construction of Peng, Rödel, and Ruchinsky. Yeah, some more letters in there. Which tells you that in a certain sense, Bourgain's theorem is best possible. So Bourgain's result isn't really a statement about Roth's theorem, right? It's a statement that, in actual fact, if you give me a set, I can find some space, in this case, Bohr set, on which I control this norm. Okay? And then what turns out to be quite a trivial argument is this norm, controlling this norm means you can control the number of three-term progressions. Okay? But that's a stronger statement than just having lots of three-term progressions. And these guys somehow show that the real theorem that he proves about controlling this locally genuinely is exponentially expensive. So that you can't do so much better than what he does if you're going to sort of output a conclusion of this shape. So very roughly, he's proving Roth's theorem, but actually he's proving a stronger theorem. That stronger theorem is close to being best possible by their construction, although the consequence of the stronger theorem we're interested in is not. Okay? And I think that's what really somehow makes this question still quite interesting, is that you have this scope, first of all, if Berend is the right construction, that you've got to find a way from your set to discover, from the fact that it has a weirdly small number of three-term progressions, you need to discover a sphere from somewhere. So that's, it seems like that would be a hard thing to do, to introduce some geometry and with no obvious geometry present, particularly if I remove the group structure, which I can notionally do with that triangle removal stuff I talked about. So you've got to find a way to introduce a sphere structure, or you've got to somehow, I don't think you can just adapt this argument. You have to adapt some argument to show that something like this is best possible. But I think I will stop there. Thank you.